Hello there, AP Environmental Science class. Welcome to part one of my lecture on Chapter 17, Water Pollution. 59 slides with this lecture. So once again, it will be broken down into two parts with part one starting right now. So as always, we look at a core case study talking about the Gulf of Mexico's annual dead zone. So spring and summer bring huge inputs of nutrients from the Mississippi River Basin. We did talk about this previously a couple of chapters ago, talking about eutrophication and things like that. That's what we're going to talk about a little bit in this core case study. So what happens is you have explosive growth of phytoplankton that eventually die and are consumed by bacteria. So basically all these nutrients rush down the Mississippi River, right, from all the farms that are out in the Midwest and in the Central Plain states. So all that nutrients flows into the Gulf of Mexico, which causes phytoplankton. They love those nutrients, right? They have an explosive growth. Well, they eventually die, and bacteria, consumers, come in to basically decompose those phytoplankton. Well, because there's so much of it, this depletes the oxygen in the Gulf's bottom layer of water, and the Gulf of Mexico's bottom layer of water. This is because bacteria, as they decompose, actually use oxygen to do that. So it depletes the oxygen. This results in a dead zone that contains little marine life because fish, other marine animals, do need dissolved oxygen to be able to live. And then what happens is in the winter, storms come in and kind of cause the Gulf of Mexico to kind of redistribute the oxygen, and therefore the dead zone goes away. This is happening almost every spring and summer here, just out where the Mississippi River ends into the Gulf of Mexico, and then obviously the water current here is moving along the coast, and so you'll notice as the nutrients go along the coast, they hug the coast. That's where your dead zone ends up being. This is a huge problem because if you live in southern Louisiana, many of you or those folks who live there are going to be fishermen, right? So when they come out here to try to catch fish in the spring and summer, they are catching nothing because all the fish have died out because of this dead zone, this lack of oxygen, because of the eutrophication or the excess nutrients flowing into the Gulf of Mexico, causing the phytoplankton to explode and to bloom. And this causes dead zones, which again, don't have any fish there, and therefore the fishermen can't catch the fish, and therefore they lose their source of income. So a very big problem occurring every year in the spring and summer near the Louisiana and Texas coast there of the Gulf of Mexico. So closer look, level of nitrates discharged from the Mississippi River into the Gulf of Mexico has tripled since the 1950s. That's because of that green revolution we talked about, right, in the industrial agriculture chapter. We talked about that. Well, obviously that is causing problems. We spoke about it in that chapter, and we're talking about it a little bit more, right? This causes the severe depletion of that dissolved oxygen. It also causes a food web disruption, right? Many species cannot migrate away from the area, and therefore they die. This causes the deaths of seabirds and marine mammal species that depend on the dying fish and the shellfish, right? So obviously you have a food web disruption or a food web collapse there. And of course, we have human factors. Dredging and straightening of the Mississippi River actually increases the flow of nutrients that then flow into the Gulf of Mexico. And what are we doing, right? We're removing those wetlands. What do wetlands do, right? They act as that's natural capital, right? That allows the filtering of pollution. By removing our wetlands, we're now not getting that filtering of the pollutions, and therefore more of those pollutants, those nitrates, end up into the Gulf of Mexico. So we're seeing this not only in the Gulf of Mexico, but in many other areas, these dead zones that are popping up. So what are the causes and effects of water pollution? Well, the chief source of water pollution are agriculture, industry, and untreated wastewater. That would be wastewater from things from either industry or maybe even possible from human waste. Water pollution causes illness and death in humans and other species. And again, as we just talked about, disrupts ecosystems by causing dead zones, by disrupting food webs, etc., etc. So water pollution is going to come from one of two sources. We call them either point sources or non-point sources. So water pollution is any change in water quality that can harm living organisms or make water unfit for human use. So what is a point source? A point source is a place where pollutants are discharged at a specific location. I'm going to show you some pictures of this. Examples would be factories, animal feedlots, underground mines, oil wells, oil tankers. Basically, it's a point, which is the source of the pollution. We can go to that point. We can see the pollution moving in, and we know exactly where it is coming from. Non-point sources are a bit different. So what we just talked about in the core case study of the Gulf of Mexico dead zone, those pollutants coming down to the Mississippi River would be considered non-point sources. You can't pinpoint exactly where the pollution comes from. They are broad, diffuse areas. Rainfall or snowmelt washes pollutants from land into surface water, like the Mississippi River. Examples: runoff from fertilizers and pesticides from croplands, logged forests, lawns, golf courses. Again, you don't exactly know where it's coming from, and therefore we call it a non-point source. So, leading causes of water pollution, again, agricultural activities, number one, because of all these excess nutrients we put into the soil to help increase our crop yields, which again, in a previous chapter, we talked about maybe doesn't increase them as much as we had previously thought, right? But because of all these fertilizers, that then ends up going into our waterways. Not only that, but sediment from eroded lands as well goes into our waterways. Pesticides, right? Bacteria from livestock and food processing waste as well go into those rivers. So again, agricultural activities, the leading causes of water pollution. Number two would be industrial facilities like power plants, things like that. Mining, untreated human wastewater, and then plastic debris comes in last as the basically where we get our water pollution from. So this is a point source, right? This is a pollution from an industrial plant. We know the source, we know the point. It's this pipe. There comes the pollution right out of it. This would be another point source. This is acid drainage from a abandoned open pit mine. Again, we know exactly where the point of this pollution is coming from. It's coming from this open pit mine. This would be non-point source. This is just sediment runoff from a farm. The problem is, as the sediment runs off into the river, you don't necessarily know if the sediment comes from your farm or from the farm next door or from the farm slightly upriver a little bit more. And that's why we call it a non-point source, because again, we can't pinpoint the exact source of the pollution. It's just coming off of off of the land into the water. Could be farms, could be golf courses, again, could be just your lawn, right? We don't know if it's your lawn or the pollution's coming from your lawn or from your neighbor's lawn. We just know pollution is coming from the lawns because of the fertilizer that you may put on your lawns to help them be greener. So, all right, those are the, again, difference between point and non-point source pollution. If you have any questions, make sure to reach out. All right, so let's talk about the harmful effects of water pollutants. Most serious threats to stream and lake water quality will be mercury, pathogens from broken sewer pipes, sediment from land disturbance and erosion, metals, and again, nutrients that can cause oxygen depletion. Infectious disease organisms also can contaminate drinking water, and an estimated 1.6 million people die every year from drinking contaminated drinking water that has some infectious disease organisms in it. This mainly happens nowadays in our underdeveloped third world countries, but obviously it could happen anywhere if your drinking water gets contaminated. So, on the next two pages, this slide and the next slide has some major water pollutants and their sources. Again, while you may not need to memorize every one, I would definitely have a general idea here of these if you need to use them on a FRQ. So again, the type of or the effect, infectious agents like pathogens can cause disease. Examples would be bacteria, viruses, protozoa, parasites. Where do we get it? Human and animal wastes. Here we have oxygen-demanding waste, deplete dissolved oxygen needed by aquatic species. This is what was happening in our core case study we just looked at in the Gulf of Mexico, right? Biodegradable animal waste, plant debris is an example. Sewage, animal feedlots, food processing, paper mills would be the source, right? Here's plant nutrients cause excessive growth of algae and other species. This also kind of is what we spoke about in the core case study with the Gulf of Mexico, right? The examples are nitrates and phosphates, which are fertilizers. Where are the sources? Sewage, animal waste, inorganic fertilizers from our farms, all right, et cetera, et cetera. So look through this. You'll notice on the second page, we have sediment that can disrupt photosynthesis, food webs, and other processes, right? Silt and soil. We just, believe it or not, guys, regular silt or soil that is eroded into a stream or into a river is considered water pollution because it blocks sunlight, which can disrupt photosynthesis, and then that can obviously disrupt food webs and other processes that are occurring in that biome, right? Heavy metals, right? Thermal, so increased temperature makes some species vulnerable to disease, right? Heat is the cause. Where do you get them? From electrical power and industrial plants. So once again, just understand what's going on these two charts. If you have any questions, make sure to reach out. All right, what are the major pollution problems in streams and lakes? So many streams and rivers around the world are polluted. They can cleanse themselves of biodegradable waste, again, if we do not overload them or reduce their flows, right? So the ecosystem service, right, very similar to how wetlands kind of take out pollution, right? Streams and rivers, as they flow, and when we spoke about this in a previous chapter, can cleanse themselves of their biodegradable waste. But again, it takes time. And if we overload the rivers or streams, then Mother Nature has a hard time of completing that ecosystem service. Adding excessive nutrients to lakes from human activities, again, can disrupt ecosystems. That's what we're talking about here. Preventing pollution more effective and less costly than cleaning it up, right? We're learning in this course that prevention is much cheaper than cleanup. So prevent it first, and then you don't have to worry about cleaning it up. So in the 1970s is when most of our water pollution control laws came into effect. One of the big issues was the Cuyahoga River in Ohio that was basically on fire. It was on fire because of all the pollution. You could actually light it and there would be fire on the top of the river. Well, this was able to be seen by people and they were disturbed. So basically, this was a bottom-up pressure from citizens that pressured their politicians to come up with laws that would help alleviate that problem. The EPA estimates that mining waste produce 40% of the headwaters of our western watersheds. That would be the rivers that we have out west. And again, the Ohio River, the most polluted river in the United States at one point. Again, but luckily that has, we've kind of cleaned that up a little bit here in this country because of the pollution laws that went into effect in the 1970s. However, in less developed countries, that's a different story, right? Half of the world's 500 major rivers are polluted with either untreated sewage or industrial waste. Water, though, is often used for human activities, so this is a big issue. Nearly half of China's rivers are too toxic to touch or drink. Liver and stomach cancer has been linked to water pollution among the leading causes of death in China. This is India. In India, they have a ritual, the Hindus, where they wash themselves daily as part of their holy ritual. But unfortunately, they also are cleaning their clothes in this river, and this river is polluted with animal and human waste. So think about that. The river is polluted, but the people use the river for their their holy rituals and to wash clothing and things like that. So you can only imagine the types of diseases that can affect these folks because they are basically swimming and using contaminated water, right? So that's a big issue, and that's something that needs to be cleaned up. So we're going to talk about now is something called an oxygen sag curve. This is what occurs in rivers when you have too much pollution. So flowing rivers or streams can dilute organic pollutants and heated water. So they can, again, the ecosystem services, they can basically clean themselves, but if they're overloaded, they can't. This does not eliminate heavy metals or slowly degradable pollutants. Oxygen sag curve is created when degradable pollutants are emitted and bacteria act to decompose the waste. So you need to have an understanding of what this oxygen sag curve means. So what we're talking about is here. Here's a river, right? And it's flowing in this direction. Here is your point source of pollution. This is coming maybe from an industrial plant or something. We know exactly where the pollution is coming in from this point, right? So over here, our dissolved oxygen is 8 parts per million. Normal clean water, trout, perch, bass, mayfly, stonefly all live there, no problems. Now you have this pollution that comes in, right? So this pollution now, unfortunately, causes this oxygen sag curve. So you have now an increased biological demand for oxygen because you have bacteria that comes in here that not only likes to eat the pollution, but also needs to decompose, unfortunately, the creatures that are dying out because of that pollution. So what you notice is the need for biochemical oxygen increases, right? And that then decreases the dissolved oxygen. So now you're in this decomposition zone to the septic zone. In the septic zone, you have the least amount of oxygen because, again, all the bacteria is using the oxygen to decompose either the pollutants or the creatures that are dying, right? So now you have an area where they have all this depleted oxygen, right? So now fish are absent, right? You only have your bacteria, maybe some worms that can live in there. It's basically a dead zone. But because a river can cleanse itself, right? That's one of the ecosystem services, some of the natural capital that rivers provide us. As we get further away from the point source of pollution, the river begins to cleanse itself or get cleaner. So now you have the dissolved oxygen demand decreasing once again back to normal levels. That then increases the dissolved oxygen, and then as a result, a number of some distance away from the pollution, you're now back to that 8 parts per million, and now you're back to normal clean water organisms. All right, so understand what happens here. Pollutants come in, a lot of bacteria. They then use the oxygen, so the oxygen demand goes up, which means the dissolved oxygen goes down. That causes this dead zone in the river. Eventually, again, the river cleans itself and the oxygen content increases once again. Okay, again, if you have any issues with the sag curve, definitely come and see me and we can talk about it. All right, we're going to move on now to pollution of lakes and reservoirs. So we spoke about pollutions of rivers. Now we're going to move into lakes and reservoirs. Lakes and reservoirs are less effective at diluting pollutants than streams. Why? Because they're not running water. Running water is what dilutes pollutants and cleanses itself. Lakes and reservoirs, most of the water is not necessarily moving that fast, and so that causes the dilution to be less effective. So what does that mean? Pollution stays in lakes and reservoirs longer. You also have stratified layers in a lake, right? With little vertical mixing. We talked about those layers in a previous chapter. There's little or no water flow. Can take up to 100 years to flush and change the water in a lake. In addition, you have that biological magnification of pollutants that also happens with the organisms that are living in the lake. So again, some terms. Eutrophication. That's when natural enrichment of a shallow lake, river mouth, or slow-moving stream caused by the runoff of plant nutrients such as nitrates and phosphates. This causes that phytoplankton or algae bloom, which then causes the bacteria to move in, right, to decompose that phytoplankton or algae, and then that causes a depletion of the oxygen. An oligotrophic lake is going to have low nutrients and clear water. We did speak about that in a previous chapter. Cultural eutrophication is just eutrophication that is occurring because of things we do in our culture, meaning nitrates and phosphates from fertilizer for farms, feedlots, streets, parking lots, lawns, mining sites, sewage plants, etc. All right, so most of the eutrophication is cultural eutrophication because we are adding the additional nitrates, phosphates, fertilizers, etc. into the water. All right, so cultural eutrophication, obviously too much of a good thing. During hot weather or drought, you get this dense growth of algae or the cyanobacteria, oxygen depleted by the bacteria that decompose the algae. All right, we spoke about that a couple of times already. How do we prevent or reduce cultural eutrophication? Well, remove nitrates and phosphates from fertilizer, right? Use more natural fertilizers like we spoke about when we spoke about food production in that chapter a couple of chapters ago. Recycle nutrients into the soil, right? Instead of just throwing out, again, putting all these nitrates and phosphates onto the soil that then gets basically washed into our lakes, into our reservoirs, into our rivers, into our oceans, etc. How can we clean up lakes? Well, remove excess weeds, use herbicides and algaecides to get rid of those, again, those plants that might be able to bloom if you have excess fertilizers. Pump in air to increase the dissolved oxygen in the lake to not allow these dead zones to happen. And most lakes will recover if excessive input of nutrients is stopped. Again, it may take a couple of decades, but most lakes will recover. So what are we looking at here? This is severe eutrophication, cultural eutrophication of Chow Lake in China. But I'll tell you what, if any of you are around or go hiking, especially in the spring, early summer in this area, any of you are golfers out there, I see this on my golf course in Spook Rock all the time. There's a pond next to the green on 6. In April and May, the pond is totally clear. By June and July, the pond looks like this because of all the fertilizers that have been used on the golf course running off into this little pond, causing cultural eutrophication, causing an algae bloom, and basically there's no fish living in that pond because of the dead zones that happen every year at my golf course. So again, you'll see this all the time if you're moving around, especially in the summer around here. Next time you see it, now you'll know exactly what it's all about. All right. Final couple of slides here talk about a case study about the pollution of the Great Lakes. So in the 1960s, many areas with cultural eutrophication, fish kills, and contaminations were occurring across the Great Lakes. In 1972, the Great Lakes Water Quality Agreement was passed. This was basically allowed for new and upgraded sewage treatment plants, which decreased algae blooms in the lake, which then increased the dissolved oxygen levels of the lake, which obviously then increased the fishing catches. So again, another positive. We realize that the Great Lakes we're having issues with cultural eutrophication and fish kills, and so we basically stopped putting sewage, which algae likes as well, right? That's fertilizer, into the water there in the Great Lakes, and that caused everything to come back. The quality of the Great Lakes much greater now. If you're wondering what we're talking about, the Great Lakes, here they are: Lake Superior, Michigan, Huron, Erie, and Ontario are 5 Great Lakes. So what happens? There's a ban on phosphate-containing household cleaners around the Great Lakes as well. However, as always, many problems still remain, still have increasing non-point runoff of pesticides and fertilizers from nearby farms. That's the greatest threat. Also, atmospheric deposition of pesticides, mercury, and other chemicals from as far away as Mexico and Russia. So yes, these chemicals can get into the air and can move around the earth and then are deposited. Rain, acid rain, things like that. 25% of the fish in the Great Lakes still have unsafe mercury content for consuming, for eating. So, Great Lakes Restoration Initiative, $1.3 billion provided between 2010 and 2015 to help continue to alleviate these problems, focused on the reducing of the toxic pollution, the cultural eutrophication, the loss of wildlife habitat, invasive species, and soil erosion in lakes, and it promotes wetland restoration, which again we spoke about. The ecosystem service of wetlands is to basically buffer between the farms and the lake, and it takes out a lot of those pesticides, a lot of those fertilizers. So again, if we can get more of those wetlands back, we can use Mother Nature's capital to help us clean up the Great Lakes. Again, the prevention approach calls for a ban on toxic chlorine compounds used in pulp and paper industry. Again, much cheaper to prevent than it is to clean up. All right, that concludes part 1 of my lecture on Chapter 17, Water Pollution. Make sure to watch part 2, and as always, I thank you for listening.